Okay. So now we're going to start to develop the field equations, or essentially, in this case, the equations of momentum balance and mass balance for a poroelastic media. And we're going to do it from a general so-called mixture theory framework. So the concepts that we're going to apply here, and in this development, we're only going to consider two species, solid and fluid, okay? But the concepts would apply for multi-species continua. So you could have solid and multiple species of fluids, say oil, water, or oil, water, air. Right? So the concepts will apply the same way, but just for simplicity, we're only going to do it for a two-species mixture. Okay, and there's going to be some other assumptions. Okay, so the assumptions here, we'll write some of them down. The big ones, right? We're only going to consider isothermal, right? So we're not going to consider energy balance. We could, just adds more complication. So we're going to consider the isothermal case. We're going to assume that there's no mass exchange between the solid and the fluid. Right? So in other words, you know, in general, you could have absorption, desorption, chemical reactions, other things that would cause mass exchange between the solid and the fluid. We're not going to consider those in this theory, okay, in this development. The other thing in the terms of the fluid flow, we're going to consider only low Reynolds numbers. That is the case when convection is negligible. And Darcy's law applies for the fluid flow. And lastly, and this is not a big deal, but we're just going to say that inertial effects are negligible. So in other words, we're just not going to carry around in the momentum equation what we're going to consider that the system is under equilibrium, and we're not going to carry around the time-dependent terms, the dv dt term, right? So we're just going to say dv dt of the solid is equal to 0. Okay. So just a couple of notation things. We're going to say that the total density is equal to the density of the solid plus the density of the fluid. And when written like this, the density, and this is why it could be, in general, I'm going to say the density of the gamma phase. And in this case, there's only a solid and fluid, so there's only two phases. But in general, you could have 50 phases. Right? So the density of the gamma phase is the intrinsic density of the gamma constituent in other words, that the density of gamma is equal to the mass of gamma divided by the total volume. Okay. So the total volume of the continua, this would be the volume of the pore space plus the volume of the solid. Okay. And another way that we might write this is that the density is some volume fraction, some volume fraction of the solid times the density. And now I'm going to use this subscript. This just implies the true density, right? Okay, so that would be the density of the solid divided by the volume of the solid. I'm sorry, the mass of the solid divided by the volume of the solid. Right? Plus, what? I'll write the equation down so to clarify. So some volume fraction times the density of the fluid, right? So in this case, we're talking about if I use a subscript, then the subscript gamma is the mass of gamma divided by the volume of gamma, right? So in this case, if you're talking about the fluid, it's the mass of the fluid divided by the pore volume. If you're talking about the solid, it's the mass of the solid divided by the volume of the solid. And these phis are the volume fractions, so they're numbers between 0 and 1, such that they got to add to 1. Okay. A couple other things I want to point out is that we're going to do this for finite deformations and then linearize it at the end. And we'll solve equations in linear form. You know, when we go to do the computing, we'll solve things in linear form. But for now, we're going to formulate everything in terms of finite deformations so that you at least have the theory. Okay. So when you have finite deformations where you have a reference in a current configuration, we're going to assume that initially the reference and the current configuration of the fluid and the solid are one and the same. Right? So you could have, you know, a big X of the solid and a big X of the fluid in the reference configuration. Okay? But when they deform, they don't have to deform according to the same trajectory, right? So the solid, I guess I should point out that, you know, here the domain of the solid is the solid line and the domain of the fluid is the dashed line. So after some deformation, the trajectories of the two don't have to follow the same trajectory. And so here you could have little x of the fluid, little x of the solid. And like you could actually have other fluid that makes its way into the solid. So fluid that's not initially not in the reference configuration of the solid could transport partially into the solid, right? And so what we're going to do when we formulate the equations is, because the trajectory of the solid is well defined in terms of back to a reference configuration, right? All real materials are going to obey the fact that the determinant of the deformation gradient is greater than 0, right? So it's going to be always an invertible. You're always going to have an invertible trajectory of the solid, okay? So what we're going to do is we're going to define the problem. So the problem is formulated on the trajectory of the solid. And so we have that x of the solid is a function of x of the solid and big X of the solid. And because we're going to formulate the problem on the back of the trajectory of the solid, we're just going to drop this, in terms of the deformation gradient and other things, we'll just drop the subscript. So, I'm sorry, these are all vectors. So we're just going to drop the superscripts on the solid. So anytime you see big X or little x like this, we're talking about the trajectory of the solid. And this is also due to the fact that solids are most naturally represented with, or conveniently represented with respect to the reference configuration, and fluids are conveniently represented with respect to the current configuration, okay? So when we write, this is really going to come into play when we talk about the mass balance of the fluid. So in terms of the mass balance of the fluid, we're going to write it in a way such that fluid can flow in and out of the current configuration of the solid, okay? So using the law, the sort of mixture theory, the laws of the mixture theory, we're going to say that the total Cauchy stress is the stress of the solid, and this is the partial stress defined on a volume of solid grains. And this is the partial stress defined on a volume of pores. So this would be the volume of the solid and the volume of the fluid, such that the total volume is equal to the volume of the solid plus the volume of the fluid. So in this case, we're also making the assumption that the fluid fully saturates the pores. Okay, there's no air in there. We could follow the same logic, but we'd have to add a third species, volume of the air. But we're going to do things more simple. Okay. So the fluid phase Cauchy stress is isotropic. We talked about this earlier, really. That means that there's no shear resistance. So the pressure of the fluid times the identity matrix is equal to the solid stress. We wrote this equation earlier. It's just now I have a superscript on it indicating that it's fluid. Or we can write it a little bit differently. Or in terms of the volume fraction, then what we're going to have is 3 over the volume fraction of the fluid. And now I'm going to introduce the trace operator. So the trace is just the sum of the diagonals. So all of those are equivalent statements. Now, returning to our effective stress, right? So we have the stress of the solid is equal to some effective stress plus alpha times the pore fluid times the identity matrix. Let's kind of switch to a matrix notation here. Or the stress is equal to the minus this guy. Okay, so everything so far is written in terms of Cauchy stress, but remember, solid materials are better, it's more natural to write them in terms of a reference configuration. So when we had a momentum balance equation in terms of the reference configuration, we used a different stress. You remember that, what that stress was called? Piola-Kirchhoff stress, right? So recall, if you go back in your notes, and I went back and checked to make sure that I actually defined the nominal stress, right? The nominal stress was J times F inverse times the Cauchy stress, okay? And the transpose of that, the transpose of that is equal to the first Piola-Kirchhoff stress, so 1 pk, right? 1 pk. And so then I have to transpose this relationship, so J F inverse sigma transpose is equal to J. Remember, J is just the determinant of F. Right? So it's not a tensor. We pull it out when we take the transpose. And then we have the transpose times F inverse transpose. Well, I didn't name it at the time, but this is called the Piola transformation. So you just may hear me, I'm giving it a name now. So in the future, if I say Piola transformation, this is what I'm talking about, right? Multiply by J and F inverse transpose on the right. All right. So now if we plug in our definition of effective stress into this thing, right, then we get that the first Piola-Kirchhoff stress is equal to the first Piola-Kirchhoff stress prime, so like the effective first Piola-Kirchhoff stress, minus J alpha PF F inverse transpose. So I just plugged in my, the effective stress relationship is in terms of the Cauchy stress, so I just plugged it into my Piola transformation. And then, by definition, the first term becomes the effective first Piola-Kirchhoff stress. And the nice thing about this is that the effective first Piola-Kirchhoff stress is not a function of the pressure at all, the pore pressure at all. So we can update this guy in terms of a normal, in general it would be a function of the deformation gradient and internal state variables. So we can update it via an elastic plastic constitutive model if you want. Right? Yeah. What? Oh, it's the same, sorry. first Piola-Kirchhoff stress. So if we then write the momentum balance down for the solid and the fluid, again, according to those assumptions that we started with, which means inertial effects are negligible, we're going to have the divergence of the first Piola-Kirchhoff stress of the solid plus the density of the solid times the body force, so this would be like gravity, plus HS, and that's going to be equal to 0. And I'm going to talk about what HS is in just a second. But we'll also write down the momentum balance. So we're just we're writing down a momentum balance on the solid, and then we're going to write down a momentum balance on the pore fluid. So HF and HS are interactive body forces per unit reference area reference volume per unit reference volume exerted on the corresponding phase or species. So in other words, HS is the interactive body force exerted on the solid, and HF is the interactive body force exerted on the fluid due to drag, lift, virtual mass effect, history effects, and relative spin. And the most important thing is that they balance internally. So that HF plus HS is equal to 0. And so with that, then we can write our total momentum balance is equal to this. We used our definition that the total stress is the sum of the two. And so this is the balance of linear momentum. And it doesn't look all that different. But next time we'll talk about mass balance, and it will look quite different. I mean, ultimately it's the same equation, but after all the manipulations, we're going to end up with a system of equations where the mass balance will look quite different than what we've seen. All right? So we'll stop there. So